these notes talk about acids and bases, and specifically looking at pH and what pH really means. So in class we did a demo with liquid Drano and lemon juice, just trying to identify common things in our houses that are acids and bases, and what happens when we mix the two. To identify acids and bases, a very common technique is using something of an indicator, and an indicator will often change color based off of how acidic or basic it is. What we are using is a universal indicator, and we say universal because it shows the whole pH scale. It goes from 0 all the way up to 14, whereas some of them only look at the acids or only change in the presence of a base. The universal indicator has varying degrees of color. So you can see here that an acid or something with a very low pH tends to be more red in color, and it works its way up through yellow to green, which is more of neutral, and then towards the blue and purple of a base. Okay, so what is an acid and what is a base? And these are simple definitions that you can look at the formula and be able to identify. So if we look at these two lists, we can see that the acids tend to have this H present, or more than one H when you look at the H2SO4. Bases have an OH present, and that really indicates what is an acid and a base. It's the production of these H's and these OH's when we involve these with water. So acids give H+, bases give OH-, and you can see that they're highlighted here. So looking a little closer at the acid, what we say is there's this supply, this H+, that is coming from our compound that's being released into the solution. But that's really not what's happening. So the H+ doesn't really like to be by itself. So what we see is we have HCl. Once we put it into a solution, it's going to break apart into H+ and Cl-. Now, this H+ doesn't like to be by itself, so we have this water molecule with its oxygen and the hydrogens, and this oxygen, remember, pulls the electrons from hydrogen. So this guy, remember how we said it was slightly negative and this end was slightly positive? Well, this negative here and this positive here are attracted to each other. So what happens is we have an oxygen with its attached hydrogens of water, but then we also have this other H+ that kind of floats around on it. So we have an H3O+, because that hydrogen has added itself to water. That we call, so this H3O+, we refer to as a hydronium ion, or the H3O+ ion. And when we talk about acids, this H3O+ and H+ are interchangeable. We can use both when talking about it. We mean the same thing because you don't really have acids without water, and you don't have H+ just hanging out if there's water around. It always joins up with H3O+. All right, so about the bases. Bases are a little bit more simple because we have this OH- that's put into the solution, and as our examples from before we saw, we had NaOH, and the OH just kind of broke apart. But there really are two ways that we can do this. So, for example, we have NaOH, and once it gets into solution, into the water, it'll break apart, and we have Na+ and OH-, which is fine. But sometimes we have a substance, a sample, who wants an extra H+. Maybe there's a little bit too much of some electrons hanging out in one space, and we need a little bit more room. We need another atom for those to go on to. So, and that's the case with NH3. So when NH3 is put into water, it will steal an H off of the water and become NH4 plus, and then it'll also form an OH minus. So our OH minuses can be formed just from the base itself breaking apart, or from a base stealing an H from hydrogen and then producing an OH, or stealing an H from water and then producing an OH on its own. NaOH, when you have this OH minus and another ion, we call those Lewis bases. All right, so, it's okay to just be acidic. Lemon juice is acidic, but we still can eat that and consume that. Hydrochloric acid, on the other hand, is acidic, but we shouldn't drink that. So how acidic it is, what the pH is based off of the concentration. And so we're going to go back and look at that molarity we talked about in the last unit. And we remember that molarity is moles over liters. So we're looking at the amount of stuff that's in this liquid. Before, we were referring to molarity and we were giving it the unit, capital M, and we were saying molarity equals blah, blah, blah. Well, here in the acid and bases, we're going to use brackets. So you put brackets around the H3O plus or the H plus, and then put a number, and that means the molarity of this is whatever that number is. So the brackets just kind of make it a shorthand, make it a little easier for scientists to write out these long reports that they have to do. Okay, so determining if something's acidic or basic or neutral basically is looking at the amount of hydronium ion, which is that H3O plus, and the OH minus. So more H3O plus makes it acidic. So if we have a greater number of H3O plus, we are going to be acidic. If we have more OH minus, we're going to be basic. If we balance out and have the same H3O plus as OH minus, we would become neutral. Okay, so we talked about the pH scale, and everybody wonders what does pH mean? Well, really, we're looking at that H plus ion, and we're looking about the potential for there to be an H plus ion. So pH is really how much of that H plus could be in our solution. We're going to get into some interesting math here because we're going to start involving log and base 10 measurements. And notice that this is a negative log, so that's going to affect our measurements as well. But pH is, we'll work through all these calculations together, but really what we need to understand is that pH is telling us how much H plus there's going to be available. We also have what's called POH, and as you can imagine, that is the potential for the hydroxide or the OH minus concentration. So we have pH and POH. Okay, so logarithm, dealing with it in algebra class, there are easy ways, there are easy problems, and there are harder problems. So to step through with the easy ones, to figure out pH, say if you have a concentration like this, where it's 1 times 10 to the negative second. If you have a 1 here and this number is a whole number, well, it's really easy. pH is just that whole number. It's just 2. So 1 times 10 to the negative second of the H plus ions would give us a pH of 2. So that's where they're easy, is when we have this 1 times 10 to a whole number. It gets, so here are some more examples. So we have 1 times 10 to the negative 6 gives us 6. 1 times 10 to the negative third gives us 3. 1 times 10 to the negative 7 gives us 7. Like I said, these are going the other way. If you have 12, 1 times 10 to the negative 12. If you have 1, this is really written out 1 times 10 to the negative 1, but we can put that in standard form, 0.1. Here's a 4. We wrote that originally as 1 times 10 to the negative 4th, but again, it's kind of a smaller number, so we can write that scientifically. You can do the same thing with POH. So if I gave you an OH minus concentration of 1 times 10 to the negative 6, POH would equal 6. Okay, so it really is the same thing. You're just talking about a different concentration. Now, pH and POH are related by this equation. So pH plus POH is 14. So since I have POH is 6, pH would be 14 minus 6, so pH would equal 8 on our scale. So these are just ways that we can look at pH and POH in calculation. Okay, it starts to become a little trickier when we add decimals. So if you notice here, pH is 6.4. It's not 6, it's 6.4. So to figure out the concentration, we're going to use the formula 10 to the negative pH. And again, this is all relating to the negative log of these concentrations. So going ahead and putting it in, so we have 10 to the negative 6.4, and that you can just type into your calculator, 10. Usually you need to use a caret symbol, which is like this. So I'm typing in 10 caret negative 6.4, and I like to use parentheses just so that I can see that a little bit better on my screen. So 10 negative 6.4, our concentration equals 3.98 times 10 to the negative 7th. And this is, of course, concentration, so we're talking molarity, but since we have the brackets, units aren't necessary. The same thing can be used for the hydroxide, the OH minus concentration. So again, we use 10 to the negative 4.6. Our concentration comes out to be 2.5 times 10 to the negative 5th. And I type that into my calculator, 10 caret parentheses negative 4.6, close parentheses, and then just hit equal, and it came out to being the correct answer. And here it is, just typed up nicely. Okay, so if we're given the pHs, you can try the H3O plus. So again, we're just doing 10 to the negative 5.6, or 10 to the negative 3.42, 10 to the negative 8.7. Over here in the bases, it doesn't matter if we're looking at pH or POH, we're still looking at that concentration. 10 to the negative 4.5, 10 to the negative 1.5, and 10 to the negative 9.6. The next slide will show the answers to that. So we have 2.51 times 10 to the negative 6, 3.42 times, or well, it would be 3.8 times 10 to the 4th. So here we have those answers and those calculations that you can check. One thing that I find interesting is, we have 5.6 and we're to the negative 6th. 3.4, we're to the negative 4. 8.7 to the negative 9. So before, when we say if our pH was 2, our concentration would be 1 times 10 to the negative 2nd. So they're related there and there. Here we're still getting that close. We're just not using a 1. We're using, we have to calculate out a specific number. Okay, going the other way is a little more tricky. Trying to get pH out of the concentration if the concentration isn't something easy like 1 times 10 to the 2nd or something like that. So again, remember that if the concentration was 0.001, or if it was 1 times 10 to the something, the pH would just be that something, that whole number. But in the second example here, we have the concentration being 0.00347, so we're going to have to do the negative log of 0.00347. This is where it's kind of tricky on your calculator. You have to find where it says log. Mine is in the catalog with my fancy calculator. Yours might just be a little button that is on the side, but you need to find the log, and then so you do negative log, and I come out for pH to be about 2.5 is the pH here. Okay, so converting all of these, again, we're going to do that equation of negative log of your concentration, and this equation works for both acids and bases. If I put the H3O plus concentration here, then I'm getting pH. If I do negative log and I put an OH minus concentration in here, then I'm getting POH. All right, so doing these, we are just going to do the negative log of 0.000087 for the next one, negative log of 2.3 times 10 to the negative ninth. Putting these in, we get equations, or we get answers. So 4.6, 8.64, 3.35, and 11.17. Now, looking at this concentration here of this acid, the acid has a lower pH than what a base would have. If we wanted to know the POH of this solution, we could say pH plus POH equals 14, or 4.06 plus POH equals 14. Subtract the two and I could come out with my POH. All right, so we are looking at a concentration of OH minus, but we want to know what pH is. So my first suggestion would be converting to POH using the negative log of 0.0045. And we get an answer of 2.35 for our POH. And we know that pH equals 14 minus POH, or 14 minus 2.35. So the pH is 11.65. This is a very high pH, so it's going to be a basic solution. So we remember that the pH plus POH is 14. All right, so this diagram might look a little confusing, but it's actually pretty helpful for you. So you're looking at, I'm starting with pH, and I want my H3O plus concentration, my hydronium concentration. So I just follow the path from pH down to H3O plus, and I see that I need to use 10 to the negative pH. Okay, if I wanted to go the other way, say I had my H3O plus concentration and I was looking for pH, I would do the negative log of that concentration. That's the same, notice that it is the same stuff as the POH to the OH minus. I would, to go from POH to OH minus, concentration 10 to the negative POH. And to go the other way, I would use the log. So those are the same, those are similar. Now, between pH and POH, you're just using that equation of 14 equals pH plus POH. So just plugging those in and then subtracting that number from 14. This one down here going between the concentrations is a little more challenging because the concentration of H3O plus, which if you have OH minus and you want to get the H3O plus, you're going to do 1 times 10 to the negative 14th divided by this concentration, or the concentration that you have. So we can switch back and forth between concentrations here. So we have this little handout, kind of a cheat sheet to help you go through all of your equations.